մեծ որոնական ներկայացնում ոնց որ ասել իմ կողմից ասել տարածության մասին, որը պրոֆեսոր Հայրապետյանը Հայաստանում հրավիրյալ հետազոտողներ ծրագրի կա այդ ծրագրի շրջանակներում հրավիրել, որը իրականացնում է Ձեռնարկությունների Ինկուբատորի հիմնադրամը TMI Science-ի աջակցությամբ։ Այդ հանը պարտադիր ծրագիրներ որ պետք է ասվեն։ Հիմա Վլադիմիրը այսօր ՆԱՍԱ-ի Գոդարդի Վաշինգտոնում և այնտեղ պրոֆեսորա, և Վաշինգտոնի համալսարանում նաև հետազոտող պրոֆեսորա, նաև հրավիրած պրոֆեսորի արդեն չգիտեմ որ այդ հարցը իսկական պրոֆեսորա Կյոտոյի համալսարանում։ Այսօր մեծ միջազգային թիմ ղեկավարում, որի անդամները և Եվրոպայից են, և Ամերիկայից են, և հիմնական թեման կյանքի և այն նախապայմանների հետազոտությունը, որոնց դեպքում անօրինական աշխարհից առաջանում է օրինական աշխարհ, այսինքն կյանքի հիմքը։ Եվ այստեղ շատ հետաքրքիր է, որ Վլադիմիրը այդ նպատակի համար սկսեց օգտագործել այն էներգետիկ ռեսուրսները, որոնցով զբաղվում է դեռ աշխատանքի ժամանակ, երբ որ Վիճանային համարցումանի բաժնում ընդունվեց աշխատում էր աստղերի բռնկումները, հիմա ոնց որ հասկացա, փաստորեն այն էներգետիկ ռեսուրսները, որոնք մինչև հիմա օգտագործվում են դրական կայծակներն են եւ այն որոնց օգտագործվում են էներգիան բացատրելով թե ինչպես առաջացավ օրինական նյութը, ըստ այս մեր խմբի իրենց խմբի այդպես հիմնական թեզերի բավական չի և իրանք որոշեցին զբաղվել արեգակի բռնկումների էներգիայով, ըստ որում երիտասարդ արեգակի։ Այսինքն հիմա արեգակի անկե բռնկումները և բոլոր գիտեք 11 տարվա պարբերականության մասին, բայց նախկինում երիտասարդ արեգակը ունեցավ ավելի մեծ էներգետիկ բռնկումներ և հիմա բացի նրանից, որ իրենք անում են զուտտեսական հետազոտություններ, կատարում են նաև արեգականման աստղերի ուսումնասիրություններ, որոնք երիտասարդ են, այսինքն որպես այն զանգվածի են դասի արեգակներ, բայց որոնք գտնում են դեռ իրենց երիտասարդության տարիքում, որպեսզի ցույց տան, որ իսկապես այդ աստղերի բռնկումների էներգիան բավականին շատ է, վերջին Ամերիկա մինչև 10-35 հզորության բռնկումներ, որը բավական է իրաց և այսօր Վլադիմիրը բավականին փնտրված է որպես գիտական աշխարհում, բավականին շատ տպագրվում է և ասում ժամանակի մասը անց է կազմում Ճապոնիայում, մի մասը Եվրոպայում, մի մասը նոր իր Վաշինգտոնի Ամերիկայում, մեկ-մեկ են տուն է գնում, ընտանիքի անդամները մեկ-մեկ տեսնում են իրեն։ Ես այնքան ասում և ասում որ այն մեր համալսարանի շրջանավարտներից է փաստորեն, որի հաջողություններով պետք է մեր երիտասարդները բավականին ոգևորվեն և փորձեն եթե ոչ կրկնել, ապա այն համառություն և գիտելիքների այն պատճառը, որ Վլադիմիրը այստեղ ձեռք է բերել համալսարանը և կարողացա օգտագործել այդ դիրքին հասնհամար իրենք նույնպես արել։ Այսօր նաև ասեմ, որ գիրք է տպվում, բանում Իսրայելում Գերբերգի և Վլադիմիրի Ամերիկյան միացյալ միան գիրք պատրաստում է տպագրության նույնպես, այնպես որ բոլոր ուղղությունները բավականին ակտիվ են։ Այսօր մեր զեկուցումը այն թեմա, որը դա վերաբերում է կյանքի որոններ for life in the universe. Կյանքի որոնն է տիեզերքում։ Այնպես որ լսեք Վլադիմիրին։
Շնորհակալություն։ Ես շատ երջանիկ եմ գալ Երևանի գիտական համալսարան և կոդեքսորը 30 տարի առաջ և հիմնական գիտելիք ստացել եմ այստեղ և գրական այս հայտարարում և օգտագործում եմ մինչև հիմա այդ գիտելիքները և ինձ համար դա շատ մեծ երջանկություն է այստեղ զեկուցում տալ։ Ես պետք է խոսամ անգլերեն, տեխնիկական բաները, բայց ես գրեցի ինչ-որ այլեն նույնպես գրված է։ բայց ես այդ ժամանակ որ ես երիտասարդ եմ, ես հիշում եմ դրամատուրգիայի ասում եմ, որ ամեն գիտնական, երիտասարդ գիտնական, եթե ուզում են գտնի գիտության մեջ, գիտությունը դա միջազգային երևույթն է, պետք է անգլերեն իմանալ։ Եվ վերջերս որ սկսեցի դասախոսություն տալ Ճապոնիայում, այնտեղ անգլերեն հարցը շատ կա։ Եվ դա առաջնահերթ խնդիր է, որտեղ բոլորը 90 ավել տոկոս գիտական աշխատանքները գիտելիքը կարող մենակ վերցնենք միջազգային ժուրնալներից եւ դրա համար անգլերենը շատ ինչքան շատ կարելի է անգլերենով տալ, ինչքան շուտով դուք նույնպես սկսեք ինտեգրացնել միջազգային գիտության, որ չկա հայկական գիտություն, ամերիկական գիտություն, անգլերեն գիտություն, կա գիտություն եւ սյուդո գիտություն։ Դրա համար պետք է խոսանք այդ միջազգային գիտության։ Ես այսօր ես պետք է խոսամ ոնց մենք կարող փնտրենք եւ հասկանանք կյանքի հետքերը։ Այս մի 20-30 տարի առաջ դա գիտություն չի եղել, դա եղել է ֆանտաստիկայի նման մի բան, որտեղ մարդիկ սկսել են աշխատել եւ the most bravest, the most curious scientists, they were trying to come up with some ideas, and we didn't have any funding, but now it is a mature science. So now it's a branch of NASA, and by the way, it's one of the most important questions that NASA asks, whether we can find the life in the universe, because the life in the universe is fundamentally important for all of us. This is the question, it's not only, the one question is that, how the universe was formed in the first place. The second one, the life by itself, some kind of probably a special type of matter, a phenomenon, and a process that we still study on Earth, but also we're trying to understand, reconstruct the past. 4 billion years ago, what happened to our planet, and then whether the young Earth can be represented of any other planet. So it's like your life. Imagine that everybody's your life is very unique. So if I take a person and then ask a question, whether your life path is typical, of course it's very unique, right? So therefore, each one of you is kind of an exoplanet from that point of view. It has the same chemistry because we need to have a certain chemistry, which I will talk about, and then a certain environment. So the environment chemistry creates your pathway, your life path. So that's exactly is valid for exoplanets. So that's why sometimes people say that we're trying to find the second Earth 2.0. It's impossible because every planet, planet is unique in that way. So I'm going to start with the major questions. We will discuss a little bit what is life. Can we recognize life if we find one? So that's one of the very interesting questions because now we're going to land on Mars and going to start building a base and going to really try to look for the signatures of life. And the only thing that we know is life as we know it. So can we have some kind of shadow life? Can we have something else? So that's another very interesting question. So then what makes a habitable planet? So this is the second question, that what the ingredients of habitability are so important, are crucial to make, first we have to find a habitable life and then to look for the signatures of life. And the third question is how to, what makes a habitable life? The third one is how to find a habitable life? What kind of hardware, what kind of telescope do we need? Okay, so in order to find those traces of life. Okay, and that's what now all those questions are not the field of science fiction. They're questions of real science, and I will try to address some of them. Okay, this is very young science, but nevertheless we can use the laws of physics, chemistry, biology, astrophysics together with data in order to put it together, to connect the dots and to make a picture that creates kind of like a realistic scenario to look for life. So The astrobiology is an interdisciplinary science. It's astro and sabanutsu. So at which is trying to understand the origin, evolution, distribution, and future of life in space. So, and in order to understand so many questions, so we need to complement knowledge of astrophysics together with heliophysics, planetary science, earth science, chemistry, and biology. That means that I'm pretty sure that we have here students from different walks of life, from different departments, and that's exactly what we need. We need to join forces. Because if we only take astrophysics, we're only gonna, learn about some kind of, one level of an elephant in the dark room. Okay, but we need to reconstruct an image of an elephant in a dark room, and for that we need so many people who can smell the elephant, people who can, touch the elephant, people who can understand and also can measure the sound waves from an elephant. So many different traits, so many different signals need to be recognized. So I will start with if we're asking about this question, the question is that are we alone in the universe? That's eventually the most important question, right? Because we all want to know whether we can find some other intelligent life, but might be not intelligent life. Let's start with the primitive life. For me, bacteria will be a pretty good friend, and then because I want to know whether the bacteria, another bacteria can be found, and whether the same DNA and RNA can make bacteria, whether this DNA that we have in our bodies is a universal molecule. Okay, so that would be one question to know, and it would be already revolutionary to everybody. So our universe is vast. We stand to 22 zeros of stars. And the reason that we know it, imagine that some curious astronomer, way back in 2006, asked a very stupid question. So believe me, there is no stupid questions in science. So don't hesitate to ask questions. So he said that, okay, let's take the most boring, the empty part of the space, okay, the night. Let's go in a clear night and look to find the most boring place, the most stars, nothing, completely nothing. And point the Hubble Space Telescope, one of the biggest telescopes. Now it's not the biggest, it's the second biggest. We have James Webb, the biggest. But that time it was that telescope. And look at it for like 3 weeks. And the telescope is like, bucket. Imagine that the rain is coming, and each droplet is a piece of light, okay, portion of light coming. Of course, the longer you look at it, the more droplets you will get, right? So that's the more information, the faintest object you can see. So that's this kind of an experiment brought us to the picture that we saw so many faintest galaxies, and each of the galaxies have hundreds of billions of stars. So by looking at the small, the area in the sky, we just realized suddenly that the universe is filled with the galaxies, and our galaxy is like 3/4, 75% of galaxies, spiral galaxies. So our galaxy is just average Joe on the street. And then we realized that our sun is the average Joe star on the street. 10% of all stars in our galaxy is like our sun. Because we want to know, are we unique, right? If you look for life, we want to know that whether life is a unique phenomenon or something common everywhere, right? We just don't see it yet. So it turns out that so far we find that, we live in a very, I would say boring galaxy everywhere. So the star is also, currently our sun is a pretty boring star. So it used to be very interesting for 4.5 billion years ago. Sometimes, it gives us surprises, and that's good. So, and then planet. We live in a planet. So now that, just since 1995, when the first exoplanet was, found, we found that, the life is, the rocky planets are also pretty common. So, my next slide is about, this is the Milky Way galaxy. This is, you see the spiral galaxy, that's where we are. We're not in the downtown. Downtown is a pretty messy place, right? Many cars, many collisions, many energetic processes going on. Every distant galaxy has a supermassive black hole, and those black holes, and especially when they're young, they produce a lot of emission, ionizing radiation that can be dangerous for life. So therefore, life can only be formed at certain regions called the galactic hub. Okay, not everywhere. And so see that the one question that we want to ask, and that's a new project that I started recently with the scientists from the University of Rome, is that if we can use this, understand that when the competition between the star in the planetary system and the central part of the galaxy becomes first the galactic phenomena versus the stellar phenomena. And you can see that the sun is here, okay, so it's midway in the halfway. If we imagine, the question is that can we have life somewhere here? And the question is probably not, because as you go further away from the center of our galaxy, the amount of metals decrease, okay? It gets less and less and less and less. It turns out that chemistry is extremely important. So that's how we try to understand our place in the universe. It's really our place in the universe, to understand why are we here. Here, here, but somewhere here. Okay, so that's one question to ask, which I will discuss. So the question is that now, what is life? Now that we need to understand what we need for life. I mean, at least the way we understand it. So it's according to the definition, the NASA definition, there's many definitions of life, but the one working definition that NASA takes is a self-sustaining system capable of Darwinian evolution. Meaning that at different levels, you probably can have smaller and smaller molecules. And those molecules are doing nothing. They cannot, specifically they're primitive enough not to copy. They cannot copy. They're small enough to, imagine that, if I ask a question, can you at midnight suddenly, without any advertisement, see 1,000 people near an opera, getting together by chance? Is that possible? You would call it a miracle, right? You would call it a miracle. The point is that that's what exactly the life is. It's a very complex system. It's many atoms got together, creating a structure. So we're trying to understand how to create this structure. When the many atoms work together, and then at some point they are complex enough that it's energetically more favorable to divide into two to make copies and to reproduce. Okay, reproduce, having certain memory, and then eventually follow the Darwinian evolution. So that basically they reproduce and they evolve as survival dictates. So see that we're talking about that the small cells at the size of the 5 microns. Okay, something that you can really see with a microscope. And then, so those bacteria, that's the single cellular organisms, their life, because they can multiply, they live their own life. They cannot study theoretical physics, of course, but they can, they live and they survive. And there's so impossible practically to kill them. So so the story of COVID. COVID is probably some life. It has its own independent life. And so we try to find the common ground with COVID life, COVID form of life. Okay, so and then of course, sometimes later, only about the last half a billion years, something happened, something miraculous happened, when this similar boring life started to explode, so-called Cambrian explosion, when something pretty complex, plants and animals appeared. And then bringing us to the place, okay? First dinosaurs, and then us, and so now we probably know why us. So because we want to know whether the intelligent creatures like us is a regular process or just one, say mistake of evolution, which can be the case too. And that would give us a pretty good strategy what to look for if we understand this process. So what does life, as we know it, mean? So what does it mean? So it means basic chemistry. If you look at your body, and the body of any bacteria, and your body, any. So for instance, I'll take plants, okay, as one example. It has oxygen, 77%, okay, by weight, and then carbon, 12%. So we say that there are carbon life forms, right? So in every movie, you hear that there are carbon, so this is carbon too. Okay, and then we have water, of course, over 2/3 is water, but water is the 2 atoms of hydrogen and 1 oxygen. Oxygen is pretty, heavy, It's 16 times heavier than the atom of hydrogen, so that's why we have 77 actually. Carbon 12% of hydrogen, 10%, nitrogen 1%, phosphorus less than 1%, and sulfur less than 1%. So I have here in just in case. So what you can see, this is the most important chemical element. So we have over 118 elements, but you don't need all of them in order to have life. At least to have functionality of life, to create life and for life to function. Okay, so you need basic building blocks, the Legos. When you play Legos, so that's you take those Legos and you start putting them together and see what kind of molecules to create out of basically, I would say dirt, like a dirt stuff. So this is we call this schnapps. It's CHNOPS. At least that gives us a good idea what kind of fingerprints and what chemical elements to look for. Okay? And how to create out of all those individual atoms, how to create molecules. The second question, of course, water. You cannot have, if you have this chemistry, you have to put this chemistry, okay, in water. So the water is probably the best solvent of life. So that's why the first question of NASA, let's say, was Mars missions, was to go after water. So you can find water, probably we can find life. Like on Mars, we have some, tomorrow I can talk about it. We have those really hard evidence now that the water was present on Mars, okay? And it wasn't like for a day or two, it was for some prolonged amount of time. So the water is another important ingredient. So therefore, that's another thing that we need to look and to understand, at what conditions water can exist in liquid state. But we don't need ice, we don't need vapor, we need really, water that we drink every day. And then the third component, rocks. You need rocks. You need rocks specifically to catalyze chemical reactions. It's that has ingredients like iron, manganese, zinc, boron. Okay, those important elements. So now that we're doing a lot of applied chemistry experiments to show that if you don't have metals, then your reactions will go so slow, then nothing interesting will happen in million years. But we know that life starts quickly. So basically, there's three major ingredients that you will look for. Basic chemistry on the planet, water, and rocks. And of course, another fourth component that I can talk about, so you would need a star. That gives you support, which supplies energy. So, happy stellar family is needed in order to have life. Okay, so you need happy family that between the star, which is the parent, and the planet, which are basically kids of this. So you need to have these interactions and the mutual understanding and mutual respect in order to have life. Otherwise, you can have a lifeless system, and probably most of them are lifeless. That's very true. So see that as basically there's 8 planets in a solar system, and that's the only blue dot that has life, right? Our Earth. So it looks like that Venus probably was habitable. Now we're studying this question, and Mars was habitable. So that's two planets. If we find some kind of signatures on Mars, of life on Mars, then the second data point, well, we have only one data point. The second data point will be enough in order for us to say that, well, probably, if n is equals 1, n plus 1, also by deduction, probably will work. So a rocket planet like Earth is required. Okay, with metals. The second one, thick atmosphere and temperate climate. So you need thick atmosphere. See that here we have an atmosphere, so-called one bar atmosphere. Okay, so the question is that if you have an atmosphere like 100 times less, is that possible to have life? The answer is no. Because at that point, water is not present in the liquid phase. Okay, so like on Mars. So that's why Mars' atmosphere is 160 times thinner than Earth's atmosphere. It's light on the planet today. Okay, so but it doesn't. But on the surface, it doesn't mean on the ground, a few meters down, the bacteria cannot. The pressure is much higher. Those bacteria can feel happy. But that's a different story. So a star like our sun is needed that can provide energy and sustain these conditions for the thick atmosphere and temperate climate. So those two things. And see that if the star is too active, it's bad, because imagine that the star is providing a lot of ultraviolet radiation. It can, promote the escape of the atmosphere. At some point, if your star is too energetic, too active, so then the atmosphere not be, will be escaping, and even the volcanic activity cannot help. So that's why we're trying to find the right balance between the star and the planet. So the real revolution started just in 2009 and lasted for 3.5 years, but it's still going on. But because with Kepler and the Kepler Space Telescope was a telescope that again was a very interesting idea. That imagine that was actually was created in the garage. It's not only that Google was created or Facebook was created in the garage, but Kepler Space Telescope was also created in the garage. Barucki, from NASA Ames, he wrote a proposal for the photometer that will look for this. You see that as the planet transits the star. Okay, the planet will be much smaller. It will create a tiny drop of light, a reduction of light. So if we can see this, if we can detect it with the sensitive instrument, then we can, and if it can happen periodically, then we can say that that's probably a planet. Okay, so he gave this idea, said that, well, I can use this instrument, but NASA is a very conservative place. And so that's why he submitted 3 proposals, and he lost. He didn't get money. So you know what he did? He spent his own $10,000 to build basically the working version of the instrument to show that it's possible. And only then he got money, and now it's a revolution. Okay, that's how revolutions work. So that's a good lessons for you. If you didn't get funding, the first time, don't worry about it. So try. Science is a very, very difficult business. Sometimes you feel that you are unfortunate, it doesn't work, but it will. So this is a very important telescope. What is important? Imagine that the idea was of this guy was just to look at the one, part of the sky. It's in the constellation Cygnus constellation. To look at more closely, but stare. Imagine that if I take you, like any person, let's say you. What's your name? Hike. I take Hike, and I look at Hike, like space. Imagine for 4 years, every single second. 4 years. Can you imagine? No breaks for lunch, for dinner, for restroom, for just looking at him every single second, okay, and getting all this data, and in 2 dimensions, his face, and looking at all his emotions, what happened. Imagine how much information I can learn about him, right? I can learn about a lot of his emotions. So that's exactly how we learn about the life of a star. We want to know, and imagine that each pixel is like one star. So by looking with this telescope, just staring, not just staring at it for years, you can get information about 170,000 stars. Okay, so that's how we got this, the treasure of information about exoplanets. So my next slide is a movie where shows you it's a Kepler zoo of 5,005 exoplanets. So now we had only 8 just in 1995, our exoplanets, our planets. And now we have 5,005, and every day we get more and more and more and more planets. So you can see here, this is the color that represents the temperature, and so the blue is cooler planets, and the red are hotter planets. See that to 1,250 degrees. It's kelvins, but imagine that. So it's approximately like Fahrenheit. So sorry, Celsius, but we use kelvins in science, not Celsius. The 0 degrees is 273. But so you have to subtract this number. But still, approximately that's a good representation of Celsius too, for you to understand. So you can see that a lot of exoplanets are, you see blue. Some of them are blue, some of them are red, some of them are bigger. So I'm beginning because this is very important. Moving. Look about. See, you have different words. This is our solar system. Look how big it is. It's huge. So the distance between us, between us and the sun is 150 million kilometers. And here we're talking about, or 1 astronomical unit, and here we're talking about not the 10%, not the fraction, but the 1%, and less than 1%, 0.5% of an astronomical unit. Imagine take our Earth and move it at a distance of 20, 30 times closer than we are to the sun. What's going to happen? That's a good question, right? And most of them that we can find, most of them, you see that most of those planets are, some of them probably happy, some of them unhappy, I don't know, but we're trying to find. Now we have the ways to find whether life can be, or thick atmosphere is one of the conditions for life, can really be, prospering and can really be, continuing for a long time. So now, so here you see that whole demographics. So because of so many exoplanets, we know that percentages. 30 of the exoplanets is the gas giant planets. Okay, it's like Jupiter. Oh, by the way, if you go to nuclear night today, it's a very interesting opportunity for you because the Jupiter is closest to us in like 50 years. So it's the brightest object in the Helium. There's only one object. It's Jupiter, nothing else. But still, take your telescope if you have one and enjoy. So 30% of all of them are Jupiter. So 31% are super Earth. The super Earth is some strange exoplanets that we don't have. It's something that we discovered, some weirdness that we don't have it, but most of the systems do have it. So, and 35% are Neptune-like, and 4% are Fish. 4% are rocky planets. So 4% of them, 5,000 or 200. So we have now information about 200 planets like our Earth. So it's a real number, right? And the question is that now that we know that 200 of them are rocky planets, the question is that which one of them can support life? So, and to understand this question, as you remember, I said that the question of the water as a solvent of life, that's one prerequisite for life. So therefore, we want to know what is the surface temperature of those exoplanets. If it's too hot, then water exists only in the vapor, right? As a vapor in the gas state. If it's just right, then you can have between temperature between 0 degrees Celsius and 100 degrees Celsius. Then you will have a liquid state. If it's too cold, then you're going to have mostly ice. So therefore, we want to know at what conditions we can have this kind of green zone. Okay, green zone. So therefore, you can see here the different stars. That have different temperatures, different masses in our galaxy. They have different luminosities, so they produce different amount of energy. And depending on that, for some stars, other stars, the green zone is farther away than we are. So this is the sun-like stars, it's around 1 astronomical unit, between 4.8 to 1.2. So between Venus and Mars, which is actually still green zone, and the cooler stars, the green zone is very, very close. Okay, the 20-30 times closer to us. So basically, that's what we understand now. That if we discover an exoplanet in the green zone, we go, wow. Every time that we look at the literature, the NASA message that we found another planet that happens on something. What we normally find is those guys. It's pretty close to the star. Okay. So next, we need chemistry. Right? I was talking about we need chemistry. So the chemistry in the atmosphere. So what is the most important and abundant gas in our atmosphere? Is nitrogen, right? In hydrogen is azote. So nitrogen. So it's a 77% of nitrogen. Do you know why? Why it's 77? Why it's not 7? So this is one question that I asked about 5 years ago. And I think that I know the answer. And so the point is that nitrogen is the most geochemically stable molecule. Okay, it's very hard. It has 2 atoms. Very hard to destroy. Okay, you need very high temperatures, so you need Kaitak in order to destroy it. Okay, so when you have a Kaitak or you have like a lightning, then you can do it. That can happen. But it's not that easy. So therefore, you need nitrogen, and nitrogen can only be produced during the subduction, during resonance. So therefore, the more dynamic was for billion years ago, the more nitrogen it will produce. And now we know, look, one question. Venus has 3 times more nitrogen than we do, okay, in kilograms. The question is why? So that's also another question that might be, we can talk about that later if you're still awake. And so basically nitrogen, that's one thing, the one gas, and then, volcanic activity creates carbon dioxide, creates water, and you have the and methane. So this is the most important carbon dioxide. Basically speaking, everything that you're formed with, you're volcanic, we are all volcanic ashes. We're made of volcanic ashes. So the volcanoes were very, very important component of our life, of our atmosphere. So the carbon dioxide, that's one gas that we need to look for. So therefore, the one prerequisite is that if we have nitrogen, we have carbon dioxide, we have water, we have methane. There's 4 prerequisites. The question is, can we create biologically important molecules? Can we create some building blocks, Legos of RNA molecule? That's one question that I'm interested in. Okay. So that question, when I asked about 5 years ago, I thought that I'm a little bit, optimist, not even optimist, idealist, or might be, I'm dreaming a lot. While I got an email from a scientist from Hong National University said that, let's do experiments. I think that I did some experiments with energetic particles, and we produced amino acids. So that's how my long-term collaboration started with Hong National University, with people studying the biochemist. So I learned about biochemistry myself and realized that without putting it all together, I would not be able to understand phenomena of life and how to look for it. So therefore, as you can see here, we need volcanic activity and earthquakes. Those things. And of course, the young Earth was much more dynamic planet. So then we can start. So what do you see here? You see our sun. It's a very unusual picture, right? In the face of our sun. But you see that it's very kind of like a hairy star. Okay? It has a lot of things you can see in the magnetic fields. And those guys are, when the energy of strong currents, we're talking about billions of amperes, get converted into the thermal energy and kinetic energy of very hot gas, heating gas to a few tens of millions of degrees, forming those things, those beautiful things as you can see. Those called flares. Okay, those huge eruptions. And those eruptions, so we have them from time to time. What happens then? So those eruptions sometimes come with ejections of, you can see this flare, the ejection of the clouds of magnetized plasma, the gas with temperatures over 2,000 gallons per second. So we have this clouds moving in different directions, and sometimes they hit the Earth. They hit the Earth and they hit the magnetic shield called the magnetosphere. So therefore, in order to understand life and how the sun affects our life on Earth, we need to understand this very delicate relationship between our planet and the sun. Okay, and specifically the so-called coronal mass ejection. This is data from the stereo satellite. So that's basically what happens. So we have a flare, and then we have a huge cloud that, and our Earth is right here. So if we're lucky or unlucky, sometimes we're unlucky. So this cloud moves too, and then it interacts with the magnetic shield, and something interesting can happen. So that's what we study, so-called space weather, or тиезерական եղանակը. It was what the եղանակը mixed it, there's no common, but the տիեզերական եղանակը is a weather between the sun and us. Okay? It affects different layers of the atmosphere, and affects believe me, technological life on Earth. And our sun then shows big flares. We know that 1,300 years ago was a flare, 775 AD flare that was really strong enough that can create havoc for us. So the space weather is now high priority for for NASA and for the U.S. administration, because they expected damage to the world economy $2.2 trillion. So anyway, but imagine that it's pretty far away, right? But imagine if you take us 23 times closer. what kind of effect will be. So therefore, those interactions between different components of our sun, and the Earth, which is surrounded by a very strong magnetic field. So that's another thing that the planet needs to have. Okay, this is the protector of life. So for instance, Mars practically has no magnetic field today. So therefore, we need to look for the signatures of magnetic field on the planet. That's another interesting problem. Now, in order to understand what happened to our planet 4 billion years ago, we need to look back. So this is the snapshot of our life, 4 years of life, for one star, resembling our sun 4 billion years ago. Okay. So imagine that you have a star that has all the characteristics that our sun, but young enough, and this is, each data point is 30 minutes, and that's the Kepler Space Telescope stares at it for 4 years continuously, and you can see the active photon. Okay, so the red one, it's the star spots, those very concentration of magnetic fields, and the blue ones are flares, and those the larger the peak, the stronger the flare, so-called super flares. You see that how many of them? You can see that how many of them we have. So that's why we start with super flares in order to understand the frequency, energy, and eventually the impact. So those flares, they create those current mass ejections. This is one of the simulations that we have done that can create those ejection of the flux source of the magnetic field with high velocity, producing strong shock waves in the space between the sun and us. So, and that's the so this is our magnetic shield, magnetic sphere, and imagine that you have a cloud coming from there. So this distance is normally 10 Earth radians. Okay, it's about 60,000 kilometers from the ground, and we're safe, being very far, all those storms. But imagine that you have a very strong storm coming. Look for collisions from here. And so that's our simulation that we explain that. So to show that what kind of a super CM we can do, see that it can basically for the couple of days can open up the magnetic pole and so basically break the magnetic shield. Okay, for a couple of days. And imagine that if this process happens every single day. So the question is that how it will affect the chemistry of the atmosphere as the particles can be freely penetrate in, not at the latitude of Alaska, but we're talking about Miami, or we're talking about Saudi Arabia, close to the equator, and how chemistry will change. So that's one question. So now all this knowledge can be applied to the number of exoplanets that we see. This is one very exotic exoplanetary system. It's we have a dwarf. Well, we have a star and 7 dwarfs. Seven dwarf planets. So this is a very cold star. I mean, it's a temperature twice cooler than our sun. And imagine that it has B, C, D, E, F, G, H. So we just have those names and the letters for them. And you can see they all have more or less size of, and they're all rocket planets like our Earth. And that's a very unique system. So this system doesn't have Jupiter-like planet, doesn't have Mars-like planet, it has most of them, 7 of them like Earth-like planet. And the question is, let's look. So all of them, all 7 of them are located within the orbit, a fractional orbit of Mercury. Very, very close. The closest one is 0.6 AU. So therefore the question is that where they can be habitable. The James Webb is observing, as I speak, this planet and this one, either because they're inhabitable zone. Some, very positive people think that life can be there. So I'm not a part of it, but still we will know. So because, for instance, one paper that was submitted just about a couple of weeks ago was that this system is all 7 billion years old. In 7 billion years old, probably the evaporation, will use all the available, those gases, volatiles, that many systems like that. They're very interesting, very unusual, exotic systems, but still, we want to see whether, atmosphere, signatures of thick atmosphere can be present. In another situation, if you have a thick atmosphere, and that the one methodology is to look at younger planets, to look at younger explanatory systems with volcanic activity, despite of evaporation, volcanic activity, and atmospheric activity, is still pretty intense, so that it can, sustain thick atmosphere. So we have the synergetic particles, forming in the so-called stellar energetic particles with energies up to tens of giga-electron. So it's a very, very high temperature. What happens as those protons, let's say, picture again, they start forming those different particles that I'm not going to talk about, but eventually forming electrons. And those electrons, they start to collide with with nitrogen, and start to destroy them. Remember I told you that so hard to destroy them into the atomic azote. As soon as you have this atomic nitrogen, then atomic nitrogen is very friendly. All those guys, when you kick out one of the atoms, it becomes very friendly, start to form molecules that are required for life very, very quickly. Okay, so that you need those so-called free radicals in order to create molecules prerequisites of life. Okay, so basically this is the process, and as soon as so this is physical-chemical matter happens here, which can be explained by physics very well. Then we can have so we have first we have N2, CO2, we have azote, carbon dioxide, methane, nothing else. And we start to dissociate them into smaller pieces, CO, CN, and so on. And small pieces are starting to interact and create very interesting molecules. First they create nitrous oxide. It's a laughing gas. We go to the dental office, and so you feel good when the procedures made normally. So nitrous oxide is the gas is a greenhouse gas. 300 times more potent than carbon dioxide. So it's a good to have temperate climate. And then hydrogen cyanide. Hydrogen cyanide is the center point molecule in order to create interesting, important molecules of cofactors of RNA molecule. So if you take 5 of those guys, okay, so you can create adenine, let's say, a very, very good molecule. So now, as we speak, people are using all these molecules in the laboratory. So we have theories. But we're now doing experiments to create, and we already created this and this and this. Nitride, as formaldehyde, that's another. So as soon as you start accumulating somewhere, small pumps, okay, somewhere in Hawaii, a lot of hydrogen cyanide, formaldehyde, then you have a pretty good chance to start forming very interesting complex molecules. At least that's what not only theory, but mostly experiments shows. Because the theory sometimes at a certain point is not very efficient in order to explain the whole chain of processes of the complexities of polymerization from the smaller guys to the bigger guys. So now looking for what planets can be really habitable, for the planets that have thicker atmosphere, is the TMI 700T. So that I was reporting that paper, and so at NASA they call me a killer of life. So the big killer. Because, every time that I look, I'm very pessimistic. I say, well, this condition is not met. But this is the one that I really like, because this is at the distance of almost 16 AU, which is 3 times further away than normally the planets are found. And all those ionizing radiation fluxes go as a 1 distance squared, or basically 10 times less. And the star is pretty quiet. Okay? So therefore, and it's mind you about 1.5 gigayears, so gigayears old. So that means that the star is young enough and the planet is young enough to generate a lot of gases that fall down. And so all those conditions make it possible that this system, which will be absorbed by the James Webb telescope probably in 6 months, would be interesting to find whether this planet is the one, the golden planet for us. how to search for this head, for the head. So, as I said, now you know. You basically, the carbon dioxide, water vapor, oxygen, we have here, right? Then I'm pushing that. So, you know that the oxygen is very bad. We have here about 21%, and we still live with it. But it's the oxidizer. And so I don't know how we eventually found a way to live with this very poisonous atmosphere. But it doesn't mean that we need 21. Some plants can have 10, and still people can be happy. So it's only what we face, as we adjust. But the question is that whether this appearance of oxygen with photosynthesis, that's why Mr. Green, is a requirement, fundamental requirement of evolution, or is just a free evolution. This question is still open. So therefore, for me, for instance, I'm a little pessimistic about it. Not pessimistic, agnostic. I don't know. So one data point, but what I know is, of course, and the methane is the case, because the first microorganisms, so bacteria, and the we know about them, are metabolism. They were absorbing carbon dioxide and releasing methane. The Helios is very smelly place, okay? A lot of methane, not a nice place to live. And we have location, but still, if we look for methane, methane is is being destroyed very easily by UV emission. So therefore, if you still find it, that means something is producing. The only way to produce it in the big quantities is life. So therefore, we find methane, and if you find, let's say, water vapor together, in the normal conditions with no life, you're not going to have methane. Okay, so so-called equilibrium. And the life is not an equilibrium; it's the disequilibrium. The same like I said that we have 1,000 people near the Opera Square. It's a disequilibrium, right? In equilibrium, you probably have few of them coming back and forth unless someone organizes the meeting. But so the metabolism, that's one thing. Where it was prevented in form of life in the first billion of year. First billion years, so-called the boring period. So therefore, the one strategy will be to look for methane. The second one, to look for water vapor. If we have enough, technology. And the nitrous oxide, that's the one that the greenhouse gas that will allow liquid water to be present, even the planet is slightly further away. So from the start, oxygen, as I said, it's only the recent discovery of the evolution only for 2.5 billion years ago. But 2 billion years ago, the Earth was lucky without oxygen at all. It was Hylarian. So that gives us a pretty good idea what to look for. And in order to get an idea, how the biosignatures look from space. So we need to look at our Earth as an exoplanet from space. And if you do, in infrared, that's what you can see. You can see so-called red jump. The red jump due to the vegetation, as the solar emission is incident to gets reflected from the vegetation. Most of the yellow and the green light is being absorbed, and the red one gets away back to you. So therefore, you're going to see some kind of enhancement of the red part. And that's so-called red age, so-called. So that's what we want to look for, red age. That's as a certain signature of vegetation. And then you see that when this picture shows you. So basically, if you imagine you have a planet, and that's a star, the light goes through the atmosphere of the planet, and part of it gets absorbed, and you can see only those depressions at certain wavelengths, at certain frequencies. And by looking at those depressions and know what fingerprints are basically are important for it, you can say, oh, okay, so that's my water vapor, that's a signature, that's a fingerprint of water vapor. Oh, that's, let's say, that methane. Okay, so we know that for certain there's a good precision what to look for. If it's planet like Earth, it has a biosphere, it's a biological atmosphere that was actually altered by light. And so this is the typical spectrum that we look for. So if you look at Venus, you see one boring spectrum. It's only carbon dioxide, and that's nothing else. Most of it. 96% of carbon dioxide. When you look at Mars, it's also carbon dioxide, 96%. When you look at Earth, you see ozone, and you see water vapor, you see carbon dioxide. It's a little bit more interesting. So, and that's what the biosignatures are, to look at the remote signatures, remote fingerprints that are created in the atmosphere surrounding the planet. So this is basically another representation with certain values in microns that will be used with the our programs with James Webb Space Telescope, which is the biggest telescope around with the 6.5 meter in diameter, with the power, total power, about 100 times more powerful than the Hubble Space Telescope. So that's why we're pretty, for instance, this is one of the recent discoveries. It found signatures of water. So those depressions that you can see are huge bands created by water vapor. So this is not a rocky planet. So we know that it's a pretty big planet. It's a gaseous planet. It's from gas, okay, like Jupiter or Saturn. So it doesn't have life because for life you need it's kind of a solid surface. And as I was talking about rocks, right? So it doesn't have rocks, but still it has water vapor. This is already a pretty big discovery. So